Tuesday, but we're gonna try to go ahead and press on. We've completed social behavior, so we've pretty much covered all of the material for that section. And again, I think it's probably better to think about social behavior in the context of really two major topics, right? So affiliation, the kind of pro-social behavior, which is a non-peptide and dopamine-mediated mechanism, and then the aggression section. So usually we sort of divide like a whole chapter like this, but I think you can best think of that section really as kind of two separate sections. That leaves us with two major topics left for the semester, which are the sort of behaviors associated with homeostasis and stress. Okay, so we're going to start with stress, and really we're going to introduce some basic terms here. So kind of the difference between chronic stress and acute stress, and we'll also introduce a concept of really eustress, which is stress that has a positive association. And so I think everybody associates stress with something negative, right? So, nobody ever says, like, that was a great stressful experience, right? Or not usually. But the thing is that without stress, right, without the stress axes, right, organisms would really not be able to respond to their environment. And what we'll look at are some commonalities of the stress response, which I think is kind of maybe best understood using a kind of larger type of metaphor. So basically, whether we're talking about a psychological stress, right, like you're worried about something happening in the future, or a physical stress, right, like maybe you have a parasitic infection or you're injured, your body essentially treats both of those things, or all of those things, in a roughly similar way. And so what we'll see with the what's called generalized adaptive syndrome is essentially the kind of calculus that the system is making. And another way to sort of think about this is if we kind of look at it maybe from like a societal level, if there's a problem, what's the first step that government does to try to solve any problem? Throw money at it, right? Because here's the thing, no matter what the problem is, it has to be solved with resources, right? So if you think about stress as a challenge to homeostasis, in order to meet that challenge, you're going to need to dedicate resources to overcoming that challenge. For an organism, really that means energy. So a lot of what the stress response is marshaling your energetic resources and making them available to essentially deal with any kind of challenge that you're going to encounter. So we're going to look at two sort of general aspects of the hormonal response to stress. So we have the sort of classic fight or flight. This is catecholamine-mediated responses, and then we have the longer-term responses, which are right through the glucocorticoid system, right? This is the classic HPA axis. We'll look at the stress response and how it relates to immune function. And again, if there's one thing that you sort of really need to start from, which is the difference between acute stress and chronic stress. Usually one is good. Acute stress is generally speaking good for the system. Chronic stress tends to result in a bunch of long-term negative outcomes. Okay, and so when we talk about immune function, notice that typically if I say stress and immune function, what do you think is going to happen? Which direction is that going? Stress decreases the immune system. That's the effect of chronic stress. Interestingly, acute stress increases both memory and immune function. And we'll kind of see this disparity between acute and chronic stress a lot over the course of the next couple of lectures. And finally, we're going to look at how psychological stress affects health. And again, generally speaking, psychological stress tends to be chronic, and thus these things tend to be rather negative. So, now, when we sort of have some general definitions of stress, notice that stressors, importantly, occur on time scales. Time is going to be a very critical component of our understanding of stress. So, when we think of acute physical stresses, if we take it from this sort of evolutionary perspective, we have things like lions and zebras. These are acute, physical, dangerous encounters, which are stressors, right? And if we think from an evolutionary perspective, this is kind of how we evolved. But there's a kind of a great book about this, that which is the reason I chose lions and zebras as our example, is there's a great book called Why Zebras Don't Get Ulcers. Now, let's think about, if you were a zebra, what would you be thinking about all day? Not getting eaten, right? So if we were zebras, and we know this because if there's something in our lives that's causing us stress, we think about it constantly, right? And if we sort of put ourselves in the head space of our hypothetical zebra, we would be thinking about not getting eaten all day long, right? I've got to go over, oh, that grass looks very appetizing, right? Well, maybe there's a lion in it. But the interesting part is that what we know from the stress response of prey animals in general is that they don't think about not being eaten all day. And we know this because essentially their stress response, they go into acute stress and come out of it, right? So zebras, unlike if we were zebras, zebras do not experience chronic psychological stress from always being under threat of predation. And again, this is going to be kind of a theme going through this. Now, the other thing that's important, I said time is always a factor. We have chronic physical stressors. Okay? These are typically things like parasites, droughts, cold winters, famines, and these types of things. And so these are the types of things that our long-term stress response was designed to deal with. Now this is a very important thing, okay? Our long-term stress response was or is adapted to dealing with things like drought, famine, especially cold winters, right? Parasites. Now, what do those things have in common? Or let's leave parasites off for a minute. What do cold winters, droughts, and famines all have in common? Well, they're environmental. They last a long time. Yeah.
Food and water.
Right. So it's an energy constraint. Right. Notice that. Right. If it's a cold winter, you have to heat yourself internally. Right. That is an energetic demand. Droughts and famines mean less food. Now, this is very critical because when we think of chronic stress, we think about psychological stressors because these things, as a general rule, probably, I can't say for sure, but I can say with a high probability that most people in here have not experienced a famine. Right? Most people, I did this in my endocrinology class. We were talking about food and energy metabolism, and I think 12 hours was the longest any student had ever gone without eating. 12 hours without eating. How long, generally speaking, do you think our ancestors went without eating on a regular basis? Days. These are numbers measured in days, right? So when we think of chronic stress, again, this is why we have to sort of think about this from an evolutionary lens. When we think about chronic stress, we're thinking about worrying about something, right? Something psychological, usually also something social, right? Like being ostracized from your group, a breakup, a loss of a loved one. These are the things we think of. But our system, right, predates any kind of psychological stressor like this. And so this is what leads to a lot of the pathology associated with stressful events. But again, we're going to return to this in just a minute. But notice that most chronic, see, I know, I still have a head injury, let's just, so I'm trying my best here. Chronic physical stressors are what our system evolved to deal with, okay? And again, the important component here is energy. Now, we'll look at the effects of psychological and social stressors, which again, as you might imagine, are very difficult to study in animals because these are things we do to ourselves. Animals don't typically experience these phenomena, although there is kind of one good model of this. All right, stress. Again, this is a physiological reaction to the perception of aversive or threatening events. Now, this is defined by the stressors invoking a stress response. So notice the stressor occurs to the organism, and the stress response is always an internal state. Okay? So the environment changes, and then your internal physiology is responding to either a real or perceived threat in the environment. And so the sort of classic definition of a stressor is something that disrupts the physiological balance, right? So hot, cold, illness, right? Or importantly, the anticipation of an event, right? Whereas the stress response always occurs sort of internal. And so that's a picture of Walter Cannon up there. So Walter Cannon is probably a physician, I think you could argue, one of the most impactful physicians in the history of the practice, probably saved more people's lives than, it would take a lot to save more people's lives than this guy. So he left his lab at Harvard to join the front lines of World War I as a combat physician. He is the one who identified and first treated shock. He is the one who identified the fight or flight response and a whole host of other things. So if you want an interesting biography, I mean, he saved tens of thousands of lives on the battlefields of World War I. So I think that's a kind of an interesting person. And he's also the person who came by and actually named homeostasis as well. This is another fun trivia fact. So, fight or flight. Now, notice that we spend a lot of time sort of thinking about what hormones mean, what the information that they convey is. And so the hormones of fight or flight are what? Epinephrine and really norepinephrine as well. And what is the information that they are carrying to the rest of the body? You're about to die, right? And so if you are about to die, how might you prevent that from happening? What would you want the system to do?
Focus on necessary organs.
Well, focus on necessary organs, right? And so another way to think about this is we want to make energy available for the things that are going to keep us alive and turn off everything else that's not going to keep us alive, right? Or is going to take energy away from this now immediate cause of our potential demise, right? So fight or flight is, okay, you have, it all comes down to the next 5 minutes, and you want everything available to you. Now, this fight or flight is a very rapid response, right? And so we typically will talk about this as the alarm phase, right, of the general adaptation syndrome. And so you get into alarm phase, and then ideally you come out of alarm phase, and this is the encapsulation of the acute stress response. If things don't go that way, then we'll be into the next phase, which we'll talk about in a second. So, General adaptation syndrome is our framework for understanding the commonality of the stress response. And it originated with, this is Hans Selye, and he was injecting rats with ovarian extracts. Now, he was interested, right? He was interested in the effects of these ovarian extracts on the rats he was giving it to. So in a classic design, he gives one group of animals the ovarian extracts, and the other group gets what? Placebo, vehicle, whatever, right? And so the interesting part of this experiment was that both the injected and the control animals developed peptic ulcers, right? Developed stomach ulcers. Now, you might say, well, why is that? Got a whole bunch of new visitors for the class today, okay? All right, so control and experimental respond the exact same way. What's happened? It was the injection itself. And so when we have looked at different experiments, you've seen sham in places. This is why you do the sham. Because what you're controlling for is the procedure itself. And so Hans Selye was one of the first people who identified this phenomenon, that the stress of the surgery or the stress of the procedure itself, right, caused a physiological response. And really this was the origin of the field of pathophysiology, right, to understand how systems respond to these kinds of injuries. And it also led to the idea that regardless of what you do to the animal is going to respond in a similar way, right? And this is why our stress response is so similar, regardless of whether it's a physiological stress or whether it's a physical stress. A little bit more sort of general info on stress. This is the idea, can stress actually kill you? And so this is the two Super Bowl cities, and so one is a win and one is a loss. This is in Los Angeles. So if I'm not mistaken, in 1984 they lost to the Bears. I don't know who, or 1980 they lost. 1984 they won, and this is cardiac deaths per 100,000. Okay, so not too long ago, Atlanta lost a Super Bowl, probably the most heartbreaking fashion that has been seen in modern times. So we can imagine that these would be similar to what we saw here in this city. So what's going on here? Now, the interesting part here is, was it the stress itself that caused death? No. So one of the kind of key ideas is it's very rarely the stress that kills you, but stress increases sort of all-cause mortality. So this is just cardiac incidences, but notice that you more than doubled on the loss, and you get a slight increase on the win. And this is a very common phenomenon that losses are, just like with the winner and loser effect, which one lasts longer? The loss, right? Losses always linger longer and typically have a much larger effect physiologically than a win does, right? And you can actually see this in cardiac deaths as well, which is kind of an interesting sort of general principle. Okay, so again, acute versus chronic, right? Acute stress tends to be adaptive and or sort of positive, whereas we think of chronic stress as rather maladaptive. Now, this is not always the case that it's maladaptive, but most of the way that we experience chronic stress is typically maladaptive. Another way to sort of think about stress is to think about this in the context of maybe going to the gym, right? So why do people go to the gym? To feel better. Okay, let's see if we can drill down slightly more than that. Yeah, so what are you in the gym for? So yes, feeling better is a sort of side benefit. Get in shape, right? So if you think about what's happening in the gym, whether you're interested in increasing like VO2 max, right? So cardio, or whether you're interested in increasing, right, muscle mass, right, or something like that, notice that what you have to do in order to achieve any of those goals, including feeling better, we'll just say that, including feeling better, is to stress the system itself, right? And then adapt to the stressor. So if we sort of take apart what that means from a physiological level, so do you have to induce a cortisol response to get a physiological change in the gym? Got some nods and some no's. Okay, so if I went in and tried to do some curls on this pen here, right, and I did this like a nice set of 10 and I put it down, is there going to be any adaptation? Is there going to be any cortisol response? No. So another way to sort of look at this is that the system is adapting to a stressor, right? So if you, for example, lifted the same weight all of the time at the same number of reps, will you eventually not stop making progress? Why? Because you're no longer stressing the system. So we kind of go back again to this. Can you get an adaptive response without the stress response? Not really, no, right? You have to induce a stress response so that is really your trigger for, right, any physiological adaptation needs to be induced by a cortisol response, right? So you have to stress the system sufficiently to generate a cortisol response in order to adapt to the stressor that you have put onto the system, right? And so we actually pay money for acute stressors, right? This is something that we do, right? And we can see all of these types of things, right? Suppression of digestion. I mean, these are typically these are components of the adaptive stress response. Now, when we think about chronic, right, you've got all of the like hypertension, diabetes, ulcers, right, impaired growth, suppression of the ovarian cycle, neurodegeneration, lots of things that are the result of chronic stress. To kind of look a little bit more in depth, you can get, and this has been sort of well studied, you can get dendritic atrophy, right? So learning and memory is impaired. You can get immune suppression. You can get adrenal fatigue or even adrenal oversecretion of cortisol, hypertension, and a sluggish response to changes in activity, and as well as the suppression of normal cycling in women or suppression of testosterone secretion in males, right? So chronic stress can and does affect really all of these various aspects of our physiology. Everybody knew epinephrine and norepinephrine. One thing to make a note about here is that if you have an epinephrine response, you will get a cortisol response. And so just so we kind of remember the HPA axis, CRH, ACTH, cortisol, right? If you have the secretion of epinephrine, you will get an increase in cortisol. The reverse is not necessarily true. You can have cortisol secretion without epinephrine, but you can't have epinephrine without cortisol. One of epinephrine's sort of, epinephrine has a fair number of effects. Notice that depending on whether you're talking about an alpha or a beta receptor mediated response, you are either constricting the vasculature that goes to something like, let's say, the digestive system or the epithelial tissue, or you are dilating, sending more blood to like skeletal muscle and brain. You are also dumping a bunch of glycogen into the system, right? You're flooding the system with glucose. Whereas your glucocorticoids, this is your slower response. This begins really about 10 to 15 minutes after the sort of start of the stress response. It's going to cause long-term elevations in glucose, and it's going to prevent inflammation, and it's going to have a few effects on sort of your behavioral responses. Now, like I said, I'm going to kind of go through this quickly. I mean, you can review it on your own. I mean, I think everyone's pretty familiar with basically the epinephrine, norepinephrine, autonomic nervous system, and again, the stress and glucocorticoids. Really, you just need to know this is your HPA axis, and the primary glucocorticoid is cortisol. Okay. Okay. So this is our sort of major framework for understanding the stress response. And so, like with many of the sort of major pieces of what we've done over the course of the semester, you're going to want to know what happens at each of these stages and have a kind of fundamental understanding of the way the stress response works through these 3 stages. Now, it's important to note that you don't go through all 3 stages every time a stress response is initiated, but typically it is a pattern of progression. You can progress from alarm to resistance, and then if you are in resistance phase for too long, then you can get into stage 3, which is exhaustion. And so the kind of model for really kind of understanding this is, the way it sticks in my mind is, let's say you put a rat in a refrigerator. You put one rat in the refrigerator for 2 hours, one for 2 days, and one for 2 weeks. What happens when you pull the 2-hour rat out of the fridge? What is its response going to be?
It's going to be
What do you think? Panic, I would say it's going to be angry, right? So it's in alarm phase. Like, it's trying to escape, it's trying to get out. Like, as soon as you open that door, that thing's going to be flying out of the refrigerator. What about after 2 days? It's not going to be dead. Maybe in a freezer for sure, right? 2 hours would probably be enough. But in a refrigerator, it's not going to be dead, but it's probably going to be, it's going to be relaxed, right? It's going to be in resistance phase. It's going to be alive, but it's going to be happy to be out of the refrigerator. It's not going to be angry. It's not going to try to bite you, right? It's going to be happy that it's been removed. Now, what about 2 weeks? Dead. Now it's dead, right? So we go from alarm to resistance to exhaustion, right? And so if it's not dead, it's going to be very close to being dead, right? And so obviously we move through these 3 stages, but we don't necessarily have to go, and hopefully not go through all 3 stages. Yes?
While they're dead, are they going to give them food, or while they're dead?
Yeah, food. You give them food too. It won't matter necessarily. Yeah, they're not dead from starvation necessarily, right? Okay, so alarm phase. This, I think, is pretty much what we consider to be the classic components of the stress response. It's mediated primarily by sympathetic activation So epinephrine, norepinephrine, which again is there to mobilize energy stores. And so I always think the easiest way to remember this is rather than epinephrine does X, epinephrine tells the system that you are in mortal danger, you are about to die. And so this is from Robert Sapolsky at Stanford. It's one of the sort of most famous stress researchers out there. So this is the stage where there's no time to be repainting the kitchen. If there is an emergency, you need to be devoting all of your efforts to overcoming that emergency. So the digestive system is inhibited. So one of the things that Walter Cannon, who I mentioned before, one of his first big discoveries was that epinephrine stopped peristalsis. So meaning peristalsis is the sort of rhythmic contraction of your digestive system that moves food through. It stops when epinephrine is put onto the system. Now, you might wonder, how did they discover that? Well, it turned out that what they were trying to do is study peristalsis in cats. So they would put cats on these X-ray machines, and if the cat was too agitated, there would be no peristalsis at all. And that was what led to ultimately the discovery of epinephrine itself, right, as a mediator of this. And now, if you just give epinephrine to any mammal, it will stop peristalsis immediately. No growth, no reproduction, immunity changes depending on how acute the stressor itself is. Notice that these are all the sort of classic fight or flight: increased heart rate, increased blood pressure, increased ventilation rate. Notice that if you get injured in fight or flight, that it takes time for that injury, sort of the pain of that injury to manifest itself. So again, classic fight or flight, acute alarm phase response. This is stage 1. Now, stage 2 is resistance. And so if you remember, the sort of main idea for chronic stress is that our chronic stress system is adapted to periods of scarce energy, right? Either you need a lot of it because you're cold and food is also scarce, or you're in a drought, famine. Notice that, so this is the hard one to understand. And I think it's only difficult because of the way that we interact with chronic stress. Because what the system is essentially trying to do is to prioritize long-term survival through conservation of energy. Okay? Now, if we think about what that means, right? We are going to, if we're not able to eat on a regular basis, it means we need to start taking energy reserves, right? So we have large energy reserves in the form of fat, but we also have energy reserves in terms of skeletal muscle, right? Skeletal muscle is essentially built up when times are good, energy is plentiful, and they can be and are taken down when you are in resistance phase. Now, why are we taking them down? We are going to use those amino acids to turn into glucose to essentially keep us alive. Now, it's an interesting sort of caveat to this, which is an interesting sort of the way that I would say that this manifests itself. So, what happens if if you're in a drought? What are you looking for? Food and water, right? So you might have to travel long distances to find food and water. So it seems almost counterproductive that we would start removing skeletal muscle if we may need it to survive. So the system has a really unique way of identifying what's okay to take, which is that if you are using the muscle actively, it's essentially spared from catabolism by glucocorticoids, right? So this is important. The way that you see this actually, in the modern world is when people are dieting, right? they want to continue to be working out, or it will, right, if your diet and caloric restriction is too significant, it'll just start taking muscle as well. But if you're using the muscle, it's going to massively prioritize either muscle you're not using or fat itself. Now, you are going to stop growing. You are going to decrease protein synthesis and increase protein degradation, we just talked about. You're going to decrease glucose uptake because you want to keep glucose circulating. And we are going to increase lipid mobilization. Now, so if we think about those conditions that we just talked about, famine, drought, cold winter, notice that at the beginning of that event, you have lots of resources. But as you go from, like the sort of metaphor here is that, let's say it's a cold winter outside, you start by throwing, right, your firewood that you've collected over the course of I don't know, fall or whatever, and you start using that. But at some point you run out of firewood, right? And if the winter is not over yet, what do you start doing? What goes in? Are you going to just not have a fire? You're going to start tossing anything flammable in there, right? You're going to start with those clothes you haven't worn in a while. But you're going to progress to, right, chairs and furniture and your bed and anything that burns over a point. But now notice that your level of resilience and your sort of spare reserves are diminishing up to a point, and they are not infinite, right? And so this is essentially, at some point, we are heating the house by burning the furniture. And you can sort of see how this is ultimately going to end very badly unless the stressor goes away. I want to make two other kind of notes about glucocorticoids, because we can't really talk about resistance phase and glucocorticoids, which, again, if I didn't mention it, resistance phase is almost completely dominated by glucocorticoids, high levels of glucocorticoids. Now, the one that I think always throws people off about the stress response is a glucocorticoid's ability to immunosuppress an individual. Right? You would think, and I think this is the sort of our natural inclination, is to think, well, if you are trying to survive for a long period of time, you would not want to become immune compromised. That seems like a terrible scenario that might actually make things worse rather than better. Right? Right? Does it not make sense that I would think that if I was going to be in a starvation environment, that, maybe I wouldn't want to just turn down my immune system to zero. But remember that what the system is prioritizing is the availability of energy. So what is the biggest energy hog, from a metabolic perspective? What takes the most energy for you? It's not the immune system. That's not number one. But it's going to be high on the list as you see where I'm going with this. What is it? Right? You guys are all biologists. What's the number one energy drain for humans? Wow. I'm the one with the head injury here. You guys are biology majors. Many of you are about to graduate. Okay, what takes the most energy of your, if you're eating 100 calories, what's taking the most energy? It's not digestion, it's the brain.
I said that.
Well, you gotta say it louder. Okay? Yes, it's the brain. Great job. The brain takes about 25% of your calories. Right? That's just, now, can we shut down the brain? Probably not a great idea. That seems very bad. The next one, I think somebody said the next one, which was muscle. We can reduce muscle demand, right, quite dramatically if need be. Right? We can not move around as much. But the third one is the immune system. And so if we think about the stress response in the context of lengthening the amount of time that we can resist, shutting down the immune system makes sense, right? And so this immune suppression, right, occurs as a direct result of cortisol secretion. It decreases antibody production, it decreases circulating lymphocytes, it decreases the production of interleukins, right, and cytokines, and these types of things. Now, we use this clinically for all kinds of use cases, right? So if you have joint inflammation, you may get a cortisone shot in the joint to knock down the inflammation. If you were getting an organ transplant, you're going to get systemic glucocorticoids. Even if you get things like poison ivy or things of that sort, you are going to get glucocorticoids to suppress the immune system. But again, from the perspective of from the perspective of what the system itself is trying to prioritize, it's trying to prioritize your ability to live for a longer time on a low amount of energy. So it is basically trying to just keep the pilot lights on and allow you to survive for longer periods of time. Okay. I think we can see where this is going, right? Which is, at some point, we are going to run out of resources. Now, notice that when we take it from the larger perspective, that all of this going to the gym so that we can feel better actually also makes us more resistant to stress. So another way to think about this process is that as we adapt to stressors, right? So if you can think of something like whether it be running, whether it be lifting heavy objects, right? It doesn't matter. The more stress you take on and adapt to, the greater challenge that you can meet in your life, right? So the more resources you have to deal with any challenge. But no matter how many resources you have, there's some threshold at which you cannot overcome the challenge any longer. And this is where exhaustion occurs. So there's no extra energy, you increase the probability of metabolic disease, increased blood pressure, heart disease, strokes, reproductive disorders, poor memory, immune suppression, and in this kind of state, this is where even modest additional stressors can be catastrophic, right? So another way to kind of think about this for kind of using using money as a metaphor. Notice that if you're really poor and living paycheck to paycheck and your car breaks down, what does that mean for you? What did you say? Did you say you're dead?
No, I would give up.
You give up? Well, so we gotta have some more resilience. You need small stressors to increase your capacity to deal with large stressors. But notice that for someone who has a lot of money, their car breaking down is an inconvenience because they have the resources to deal with it. Whereas if you have almost no money, it can be the next thing you know, you could be homeless because you can't get to your job, right? You have no way to repair your car, right? And again, it's the same stressor in both cases, but it depends on the state of the individual who received the stressor, right? And so this is why it's kind of important to build up that capacity to deal with stress. And we should never give up. Okay. So, while this is, again, described as a generalized stress response, there is some degree of specificity. So for certain types of things like hypoxia or hypotension, right, so low blood pressure or low blood oxygen, you have specific responses in the kidney and in the gastric sympathetic activity to increase essentially oxygen utilization. And in sort of hypotension, like this is your angiotensin II system with renin and angiotensin II, vasoconstriction, absorbing more water, absorbing more salt, kind of all of that stuff is unique to low blood pressure. It doesn't necessarily produce the same kind of systemic response. Now, all stressors provoke some degree of catecholamine and glucocorticoid secretion. So glucocorticoids always go with catecholamines. In many cases, right, in resistance phase, you can get glucocorticoids by themselves, right? Now, the exact response of the hormones does depend a little bit on stressors, but again, as we say, it is typically quite generalized. Have we pretty much covered all of this, right? Most of the stress response is mediated by these two hormones, cortisol and epinephrine. Again, when we are kind of thinking about this, acute is both resistance, and chronic stress is primarily dominated by glucocorticoids. I'm going to do a figure here. Has anybody ever jumped out of an airplane? One, just one? Two? Oh, two, okay. The little one too? Mom, that's an interesting choice. Okay, so did you find that experience stressful? Did you have a stress response sitting at the side of the little plane there? I say that my 85-year-old grandmother, she's older now, but she jumped out of a plane on her 85th birthday. So she's a tough one. I didn't go up there. So they did this study of Norwegian paratroopers. Okay, so these are people who have decided as a job that they want to jump out of airplanes. Okay, now notice that what we're going to do is over the course of their training jumps, we are going to measure their sort of endocrine profile. So we're measuring a bunch of things, right? We've got cortisol and epinephrine and norepinephrine. Those are part of our stress response. But we also have growth hormone and testosterone. Okay? Now, why are we having growth hormone and testosterone in there? Because those are... Okay, no ideas?
Growth hormone and testosterone. Oh, is that the HP?
Oh, I hope you got the red letter on the end of this one.
HPG axis?
HPG for testosterone, and we're gonna get, what about for growth hormone? Anyone, we can phone a friend? That one, anybody? That's HPG.
The liver,
The hepatic, there we go, the HPH. Now, we're interested in these because notice that anytime you have stressful experiences, that you get a decrease in sex steroids. And often, as you can see here, you get an increase in growth hormone as well. Now, growth hormone, at least in principle, is going to be your repair mechanism. So you want to essentially suppress sex steroids, increase repair, and then again, the rest, cortisol, epinephrine, and norepinephrine are actually part of the stress response itself. So what happens on day one? So now notice we're gonna go before, after, before, after. These are jump days. Now these are not consecutive days, but these are days of jump. So how's your first jump? Very stressful. Your first jump is very stressful. Notice how much epinephrine, cortisol, and norepinephrine we have. Okay? Also notice the massive responses that we see in both growth hormone and testosterone. How about day two, or jump day two? The blue says after that day's jump, so conceivably when they're back on the ground again.
Less stressful.
Is the experience the same? Did they do the same thing?
Yes.
Now, why did it go down? interesting. It's, so I wouldn't say it's resistance in this case. They're so how about we say they're used to it? What kind of term would we say? What is happening? They've adapted in a sense to the stress because it is. So what is causing this? What is causing this experience?
Fear.
Fear. Right? This is going to seem strange because they're doing something physical, but the response that we're measuring is psychological. Right? All of this is psychological. Right? Now, notice that by the time they're on jump day 11, they're actually as relaxed, if not more relaxed, than they started with. And because this is part of their job, they have now adapted to the social stress or the psychological stressor. Now, we are headed into the last portion of the semester, and those, right, you guys are all seniors. Does it get less stressful towards the end or more stressful towards the end? More stressful more towards the end, right? Now, we can actually kind of measure this, right? And this is what's shown over here. This was the measurement of people taking the qualifying exam. So if you go to graduate school, right, so if you're in the PhD program, the first 2 years of that, right, that's your sort of general education type of thing, and then you have your qualifying exam. Now, if you don't pass your qualifying exam, at least in the old days, I don't know if it's still this way, then you just don't come back to graduate school.
Okay.
So it's my way of saying it's important, but you could imagine how that would be stressful, right? And can we measure the amount of stress that these people are encountering here? Yes, right? And I could probably, I would say with pretty good certainty that if I was taking your cortisol every day in class and we had a time series, that as we approach the end of the semester, right, not just for this class obviously, but all of your classes, there's all these exams and projects and stuff that are all due at the end, right? So your stress level goes up, and we could measure that, right, day over day as an increase in cortisol. Another way, and I think we might have talked about this before, so if we're looking at trains, I don't know if many of you guys ride MARTA, but a crowded train is typically, I would say, much more stressful, right? And we can measure the amount of circulating epinephrine in individuals and notice the huge difference between whether you're taking a train at a normal density or a particularly crowded train, right? That you have about 3 times the epinephrine response to a crowded train than you do to a sort of normal train. Okay, so let's talk about the sort of metabolic stress response. So we talked about resources, and we've talked about them mostly in the abstract, right? So meaning that we are going to be releasing glycogen, we're going to be increasing lipolysis, and as a general rule, we're going to be flooding the system with higher levels of energy. So all of these things, glucocorticoids, catecholamines, and glucagon, are anti-insulinogenic, right? So they are preventing storage. Now, the fat cells typically will reduce their glucose uptake, and they will essentially begin releasing more free fatty acids to be converted into ketone bodies in the liver. Right? So these free fatty acids are then available for energy conversion, and this is sort of the way that we increase the amount of energy. Now, if this system stays on too long, right, so i.e. if you are experiencing chronic stress, right, you will experience myopathy, muscle wasting, and as well as chronic fatigue and weakness. If we think about resistance phase, why should you be tired all the time? Not only is it less energy, but what does the system want you to not be doing? Using energy unnecessarily. Right? So unless you're actively out foraging, the system wants you to not be moving very much. Okay, some other hormones that are involved in these things. We know some of them are obviously endorphins. We met those with the chicks, right? These activate the mu opioid receptor. These are analgesic. You have prolactin, which can and does affect reproductive physiology. So another way to sort of, and we won't talk about this very much, but prolactin, high levels of prolactin shut down the HPG axis, right? So we see this really in two major places. So notice that when females, right, whether pretty much any species, when they're lactating, they are not cycling. Right? Now it's not universally that way, but prolactin reduces the ovarian cycle by shutting down the HPG axis. So you see this as a way to shut down reproduction in males as well, right? High levels of prolactin prevent male reproductive behavior. Those can be facilitated by glucocorticoids. Vasopressin can be involved in the stress response, and so can glucagon, again, to increase the availability of energy. Okay, so things that inhibit stressors are pretty much anything parasympathetic. GnRH, LH, FSH, insulin, all of these things are going to be inhibited by stressors, right? Shut down the HPG axis, because if the environment is sufficiently stressful, it is really not the time to try to reproduce, right? A drought is not the time to try to reproduce. Now, with growth hormone, as you've seen, we have a very big difference between acute and chronic, right? Acute stressors increase growth hormone secretion. Chronic stressors reduce growth hormone secretion. Now again, growth hormone is involved in things like cell proliferation, which again, if you are in an energy conservation mindset, you want to, not really mindset, but if the system is in that sort of state, then you want to shut down growth, right? And we're gonna look at a very particular case of what's called psychosocial dwarfism, where psychological stress decreases growth hormone to such a degree that it inhibits the normal growth cycle for humans. In women, chronic stress makes or can make women acyclic. So this can be high population densities, right? Decreased food resources, and I'll show you a figure about this on the next slide. But one of the most well-studied cases of this is social subordination in macaques. And so essentially, dominant females harass subordinates to induce a chronic state of stress. Yes?
High population densities, like people in metropolis versus rural?
Generally speaking, this is mostly work done in animals, right? So if
It didn't seem right, yeah.
if you increase the number of individuals, it's like the same kind of crowded train phenomenon. Whereas if you increase the number of people, the stress levels increase and the reproduction and reproductive hormones decrease. So notice that it's not rural versus urban from our densities, because most or a lot of people, even living in high density environments, aren't living with like 15 people in like an apartment, right? That would be a stressful situation that would potentially result in decreased ovarian function for women living in that environment. Yes.
That was gonna be my next question. So what if you have like two families in the metro Atlanta? One has a family of like 12 people in a one bedroom apartment, and one has like, you know, one kid and one mom. Would you see a difference in their cycles?
You would see a difference, absolutely.
Okay.
You would see a difference, and this is really well understood in animals, right? If you increase their optimum density, they become more stressed.
Okay.
And if their cortisol raises to a high enough level, it will shut down the HPG axis for, again, as we said, for both males and females. But we're talking specifically about females here. But notice that women in high stress environments will often have irregular ovarian cycles all the way up through basically going acyclic for a period in time. But the social subordination one is kind of where we see this a lot. So these are older females actively harassing young females to the point that they become acyclic. Now, we should immediately be thinking, why are the females doing that? Why are the older females doing that? Competition, right? So what do they really want? They want sexual exclusivity of the males. And so if they harass the younger females into not cycling, then the males, as we just learned, right, in the section female reproductive behavior, if a female does not have estrogen, right, she is not as attracted to males, right? Males will not invest their resources into those females, right? And so this is an active process of really, there's no other way to describe this as just straight harassment. They will just chase the younger females around until they basically have no interest in males at all. Right? Now, the effects of exercise, this is in women. And long distance running is one of the most stressful things, like marathon running is one of the most stressful things that you can do to the body. And even long distance runners typically on a regular training schedule are not running the sort of 26 miles or so that 26.3, I think, is the marathon length. But notice the effect that this has on LH. Now everybody remembers LH, what it does, right? So notice that you have a massive decrease from, I'd say, a mean of what, like 10-ish maybe, to a mean of maybe 3, right? So that's a 3x reduction in LH, right? And more to sort of pick on marathoners. So this is a great model, because if you think about if you're running a marathon, are you generally in good health?
Yes.
I would say yes. If you're not in good health, I would not recommend trying to run a marathon. But it does provide an interesting backdrop for the measurement of stress in the absence of any other sort of physical ailments, right? Because people who run marathons are very well likely to be in really good shape otherwise. So, notice we're measuring cortisol and epinephrine, and we're actually going to measure testosterone. These are in males, obviously. And so notice that over the course, right, so we have 1.5 hour post-run. Notice that it's even a little bit elevated 6 hours after your run for epinephrine and cortisol. And you have a significant decrease in testosterone from the beginning of the race to the end of the race. And this is, interestingly, probably only one person is going to get a boost of testosterone for winning this, but it might not be enough to overcome the loss of testosterone due to the excess stress of going through this 26-mile run. So, yes?
So would it be considered acute stress or chronic?
So this is kind of one of those that are, right, so when, again, remember when we're drawing these like acute and chronic stressors, right, it's not like a hard black and white line sort of on this side, it's acute. I would say this is kind of an example of a chronic-ish stressor, right, because typically so if you think of the parachute jumpers, that's a quick thing, right, you're up there, you're stressful, notice you get that testosterone decrease quickly, right, after your jump, but that would definitely be an acute stressor. This is a longer term, I'd say it's kind of almost straddles that sort of intermediate space. Okay, I think that's probably enough stress for today. We're gonna do a number of figures next time. And we're going to sort of apply our knowledge of the stress response. Now, before we go for the day, right, you're welcome to keep packing up, it's fine. But if you would like to discuss any social, either aggression or social behavior figures for our sort of our last bit of time here. And I will have your exams on, they were almost done to start with, but I've had a little bit of an inability to look at them. Any figures you guys want to go over? It's like packing up already. I mean, that's okay by me, but.
I'm looking for the next
Yes.
exam
There's a
day.
figure on testosterone in hamsters.
Testosterone in hamsters, okay?
And aggression.
All right. Social behavior, testosterone in hamsters.
Okay.
Thinking about
I think that's it.
this one?
Yes.
Okay.
Oh, that's a tricky one.
Hmm?
That was a tricky one I was asking.
This is a
about
tricky
last
one,
time.
yeah, this is a tricky one you were asking about last time. Okay, so, what do they want to know about here?
Oh, I remember. So whether or not going through puberty has an effect on the rest of your life.
Right. Whether or not going through puberty as male, right,
On the behavior.
right, has a lifelong effect on behavior, right? That's right. That's what we're interested in, and specifically, we're going to be interested in essentially what is a measure of aggression or submission, right? Whether your lifelong degree of aggression or submission is affected by going through puberty, right? So we have seen effects like this in organization, right? But this is the first time we've seen the critical window of time for a behavior that is essentially activation, right? Okay, so if they're interested in understanding whether or not, so that's a great start to the question. So how do they go about answering this question? That's always the part that's next, right? So this is the question, so how are they gonna answer that question?
So they're observing the number of attacks and the number of escape actions, which are submissions.
Mm-hmm.
Over a lifetime from a one that's
Are they measuring it over a lifetime? Hmm?
It gets into, it's like pre-puberty and then adulthood.
Okay, so an important, this is part of the confusing part. This isn't sum over a lifetime. They're measuring it at one point in time, right? So all of these animals are the exact same age. Okay? So the only thing that differs is the timing of puberty, or the timing of GDX, right? So when they were castrated. Whether they were castrated pre-pubertally, that's the column on the left, both top and bottom panel, or after puberty. But the animals are at the same age, and the test takes place at the same age for both groups. The only thing that's different is when they were castrated relative to puberty. Right? Okay, so we can pick back up. What are the critical comparisons here?
The number of attacks and number of escapes.
Yeah. Okay, so, can you say it a little bit louder? Do you wanna try to read it before me?
Okay, the rats that were castrated before puberty were more submissive, they escaped more. And the rats that were castrated after puberty were more aggressive and pretty much attacked 100%.
Okay, now, importantly, do androgens play a role in what kind of behavior you exhibit?
Yes.
Yes.
Do they?
Yeah, puberty castration it does.
Not really, right? Not, and certainly not in the direction that we would expect, right? So again, notice that what we're doing is giving androgens or not, right? And in both of these cases. And so here, does giving androgens change the aggression of these animals?
No.
Not really.
What about here? There may be a mild effect, but if anything, giving androgens makes them more
Yeah.
submissive,
For sure.
right? Okay. So that was a good answer, right? I definitely want to. Yeah. So I just wanted to kind of build on it a little bit more because I think it's important to sort of understand with you. So when we say the critical comparisons, remember if we're asking the essential question was, does going through puberty, right, change your behavior, right? Like. And so to answer that question, we have to compare, right, the ones that were castrated as adults to the ones that were castrated before puberty. And we see marked differences, right? The ones that were castrated after puberty, whether they had androgens or not, were mostly, if not exclusively, aggressive. And the ones that were castrated before puberty were almost exclusively submissive, regardless of androgen state in both of those cases. Right? So, bring it home. What does that allow us to conclude? What is the take-home message here?
Going through puberty has an effect on.
So we don't like. So yes, if we can just pause for 1 second. We don't ever like terms "has an effect." Right? We want to describe that effect.
So going through puberty increases aggression
And
decreases submission.
yeah. So again, remember always. So we can always say has an effect. And I'm just since you said it, I'm not trying to pick on you. We always want to describe the direction of the effect because an effect could be anything. Right? So going through puberty as a male, I'd say increases your probability of aggression and decreases submission, whereas castration before puberty increases submissiveness and really reduces aggression. Yes?
So activation in those cases that we choose the behavior.
Yes.
So
And so we wouldn't necessarily have expected that. This is what the data says. The data says if your brain was exposed to androgens during a critical period of time, then your behavior will always be different, independent of your steroids at that time. Yes?
So the part about giving androgen does not affect aggression based on submission. So is that something that you want to add, like the critical?
That's in the critical, so if we think about, and again, we're imagining saying this, right, as in the context of an exam, and I think that that's important, right? Obviously, it's what you guys, it's important to care about that. But when we think about like why that's important, why is it important that they gave androgens? It's because notice that the red one over there, right? The red bars have no androgens at all. Those are just castrated males. They have no circulating testosterone. And so what that's controlling for is, okay, well, do androgens at the time matter? Or is there a, what we would call like a path-dependent effect? Do you have to have had androgens at a certain time in order to express the behavior? So this is because our question isn't so much, do androgens cause aggression, but does puberty and the hormones of puberty affect your behavior long term? Now that could still be androgen dependent or not, but it says that going through puberty affects your behavior from that point forward, right?
So
And
this basically supports the organization and the activation.
yeah, this is an example of activation crystallizing a behavioral phenomenon. Yeah. Any other ones that we'd like to go? This was a tough one. This is a tough one to understand. But the message is really important.
So what was the big takeaway, just that, stress increases cortisol?
Well, no, so I think the big takeaway for today is you want to be able to describe the 3 phases of the stress response, which hormone or hormones are active at each of those stages, and sort of what's going on, right? That our big picture. So there's that, and we're going to be drawing a distinction between acute and chronic stress. Okay, so those are our big takeaways for today. Other ones?
I have one.
Okay.
I think it's the first one, it's favorite viewpoint, and
Yeah. Okay. There it is. Yes. Okay. Is there a specific question about this one, or do we want to start off? What are they interested in here? Let's take one. Okay, so since this is, but if I were to give this on an exam, I'm going to give you one or the other, not both, right? Because it's really two. While the question that they're asking is essentially the same, right? It would be too much to have this as a single one. So why don't you pick? You tell me which one you want to pick, males or females? You want to pick females? Okay. So what are they interested in here? What is the question they're trying to answer?
what area of the brain is
Mhm.
responsible for care
We can be a little bit more specific. Yes.
bonding?
What?
Where receptor
Oh, what receptors?
oxytocin.
All right. Okay. So rephrase it all into one piece. So what are they interested in?
Where in the vernal brain are the oxytocin
That are
responsible for pair bonding?
Okay. Right. Okay. So are they looking for vasopressin receptors in females?
I don't see it.
So what drug are they giving? Hmm?
Oh, oxytocin.
Oh yeah, OTA. Yeah.
Well, she said oxytocin and vasopressin in females, right? So
Yeah.
that's what I'm just starting correct. So if we could take one more stab at the question.
I gotta go again. What is somebody else?
Okay, what we're at, what, oddly enough, that's exactly what we're asking. What is the question?
Where are the oxytocin receptors responsible for pair bonding in female prairie dogs?
Okay, great, yeah, yes, right? So, like I said, and notice that I keep harping on the question, because if we can formulate the question, we can pretty much calculate everything else. And that's kind of why I keep harping on it, right? So, the question is something along the lines of, right, where are the oxytocin receptors that are important for pair bonding in female prairie voles, right? Some formulation of that. We've heard several different ones, and they're all good, right? We're interested in what brain region has the important receptors, right? Has the important oxytocin receptors for pair bonding. Now we know that the top one is just dealing with oxytocin receptors, because really we're not measuring the receptors there. We know they're there already, but what we're doing is giving a drug that blocks them. We're only giving that drug to specific brain regions. And so we have 3 brain regions that have, so if we, as a kind of way, and I'm going to bounce over here just to make the point that these are the oxytocin receptors in the female brain. Notice the nucleus accumbens, the caudate putamen, and the prefrontal cortex are all right there. They're all black. It means that there are lots of receptors there. So we are giving, whoa, went the wrong direction, giving drugs just to those specific regions. Okay, so, and we are measuring, as you pointed out, so how are we going to do this? We're going to give drugs to the reason, and we're going to measure, are we measuring?
Time and contact.
Time and contact, right? And that's what we're measuring, huddling behavior. Okay? Now,
It's like the assignment.
Assignment, yeah.
that was in Prairie Bowls, right? So yes, Prairie Bowls. So here we're just giving the oxytocin antagonist. There, we were actually giving a virus that had the vasopressin receptor, which, if I'm not mistaken, the vasopressin receptor was put here.
Yeah.
Now, why did they put the receptor there? Because those are the important regions, right? So, staying with our females, we're measuring contact time in Prairie Bowls, and we're going to give an oxytocin antagonist to these specific brain regions. So, what are our critical comparisons here?
Time and cuddling for different parts of the brain.
Okay, so which ones would you choose to answer here? So you say, so the critical comparisons are,
Different parts of the brain.
I'm telling you no.
Oh.
I'm telling
I
you that's
missed it.
Yeah, so I'm saying when you would say, well, the nucleus accumbens, right, is different. The pattern is reversed in the nucleus accumbens. It's reversed, but to a lesser degree in the prefrontal cortex, and it is not affected by the drug in the caudate putamen. Right? So
That's
all,
the way to say that.
yes,
Gotcha.
right. Now, what does that tell us is the yes.
I'm sorry, I kind of just blanked out. So when you give this drug that blocks this area, right?
Mm-hmm.
It doesn't affect the nucleus.
Does it or doesn't it?
It's,
If you put in a nucleus accumbens, you get less typical behavior.
oh, okay, I see.
So what do you get?
A greater response.
To who?
Yeah.
You get the opposite.
Okay.
Okay? There isn't a more important point here,
Yeah.
right? So now again, when we gave combined CSF, you could just as easily say, right, vehicle nucleus accumbens, vehicle PFC, vehicle caudate putamen, right? This is your control. Everything is compared against this because this is what happens when the receptors are functional. So notice that when the receptors are functional, we spend more than an hour cuddling with our partner, right? When I give the drug to the nucleus accumbens, you pretty much don't spend any time with your partner and you go and spend all your time with a stranger. Is that not the opposite of what a monogamous female should do?
Right.
Yes. So what does that tell us about the system? How does that answer our question? Okay, great. Yes. I'd probably put a point about the PFC being important, but not as critical, right? But for sure, the nucleus accumbens is the most important part of this. Even though there are just as many receptors in the caudate putamen, but those receptors aren't for pair bonding. They're for something else. Does that make sense? Hmm?
Or are you, if we don't mention the takeaway on
If you don't mention it at all, I probably take a point or two. But again, so the general metric is that if you're getting, right, 7s and above, like 7, 8, 9, those are a good score, maybe missing a small thing, right? Less, like 6 and below, you're missing some major point, and then 3 and below, we're like not even talking about the experiment that was being done, right?
So-
Generally.
So
Yep.
it would, for males, it would essentially be the same thing, but in the ventral palate, the ventral palate, right? It's the same effect.
Yes. Yes.
And
Right.
it would be vasopressor receptors, not oxytocin.
Right.
Okay.
It's the same, it's essentially, I mean, and this is why it's shown as a 2-panel figure, it's essentially the same question, but one for females and one for males, right? And the brain regions are different, but the design, all the big picture questions is the same. But it would, as I said, it would be too much to have this as one figure, because really you could do, right? So essentially you could think of it as two figures.
I have one question.
Sure.
Can you remind me of the format for the final? Is it similar to our exam? Or is it
It's just
different?
it's gonna be like 80% figures.
Okay.
Okay.
It's just all figures and an essay on.
Study guide this time?
Yeah.
You have your exams. You'll have your exams.
Oh,
What is the takeaway message?
Yeah, that was a lot.
Okay, does somebody want to help your fellow student out here? We had some good, we did good, right? We had it. You guys have it. What's the takeaway?
Oxytocin receptors and the nucleus accumbens, as well as the TFC banana strongly play an important role in pair bonding and pair.
I would say play. I would say are necessary. Right? Right, just, again, always, wherever you can, talk about the directionality of the effect, right? Oxytocin receptors are critical for the formation of pair bonding. If you block them, you get rid of the pair bond. Right? Okay. We'll have your exams on Tuesday again. I apologize. Thank you. And I apologize for Tuesday and the not having the exams, but I will have them for Tuesday. We will discuss them at length.
Horrible. Horrible. I didn't even look at the score.
You didn't?
Of course not.
It's like one
You don't
page
have a
of film
choice. I don't have a
and-
choice,
oh,
but I get it.
I think it's because I did it after the like I started right before the deadline, and once the year's over, it's like shut it down. You're out of there. Have a good day. I never like when we take an exam. I don't look at the grade until like he tells us in class how it works.
Oh,
Yeah.
for a few weeks after.
Yeah, exactly. Like once he breaks down the curve or
I
whatever.
have to have like a happy energy.
Exactly.
To be able to like take it.
And the second one was like right before spring break. I said, I don't care. I don't want to know. I did my best. I'll see it after spring break.
Oh, I'm so nervous.
Literally. Have a good one, dude.
Yeah, I'm not gonna lie, I'm a little bit busy.